Okay, dear students, welcome to my small session on the continuation of the Schrodinger's wave equation, which was discussed in the previous video. That is, talking about significance of the Schrodinger's wave functions, wave equation, as well as the main part of this one is talking about the solution of Schrodinger wave equation. So, two things. First, I would like to discuss about the significance of the Schrodinger's wave equation. A few things like whatever the Schrodinger's wave equation we have derived, and the Schrodinger wave equation is said to be giving satisfactory results in a spherical coordinate system. In the spherical coordinate system, we have XYZ we told in the formula that XYZ are called as Cartesian coordinates. Once we solve this Schrodinger's wave equation and the wave function is satisfied by any of the functions which are discussed in the Schrodinger's wave equation, all those functions in the spatial arrangement around the nucleus are said to be eigenfunctions. They are called eigenfunctions. So once we solve the Schrodinger wave equation, and Schrodinger wave equation is having wave function which is a continuous function, and as well as this wave function has got finite values and is the integral part between the plus infinity to minus infinity. The value should be there, but at any point, the value should be, wave function value should be 1. That is one important significance. The second important significance of the Schrodinger's wave equation is nothing but for hydrogen atom, the solution of the Schrodinger wave equation and the calculated value of the energy, whatever we have discussed in the Bohr concept, the energy is 2 pi square me power 4 into k square h square by n square h square. K square n square formula is there in that. That energy value of hydrogen electron in the Bohr atom, which is very clearly explained by Schrodinger wave equation. That means solution of the Schrodinger wave equation is useful to calculate the energy of the electron in hydrogen atom. That is one important significance. The next one and the most important one for the significance of the Schrodinger's wave equation is nothing but yes, Schrodinger wave equation actually developed the quantum numbers for electron in hydrogen and hydrogen-like species. Okay, that means principal quantum number, azimuthal quantum number, magnetic quantum number. These are all developed by Schrodinger wave equation only. That means the solutions of the Schrodinger wave equation simply we can call their quantum numbers. As we all know, these quantum numbers are also giving information about that energy of the orbit. That means the energy stored in the wave function, the information stored in the wave function is energy related information, as well as shape of this orbital related information, as well as orientation of the orbital along these particular coordinates is stored in Schrodinger's wave function. That means Schrodinger's wave equation we solve means, in other way you can say, whatever not explained in the Bohr concept that are said to be discussed in the Schrodinger's wave equation. It's an advanced concept over Bohr concept, but one small information limitation of this one is also it is applicable for hydrogen-like species only. Okay, so we cannot solve Schrodinger wave equation right now for multi-electronic species. Anyway, at that time, this Schrodinger wave equation got prominence in this wave mechanics. Okay, let us discuss about this solution of Schrodinger wave equation by considering the spherical coordinate system. Okay. Now let us see this one. As of now, we have derived the Schrodinger wave equation already for hydrogen atom. That is the dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into E minus V will come. That V is potential energy. That is minus of minus is plus E square by R into psi is equals to 0. This is the Schrodinger wave equation according to the concept of Cartesian coordinates. Okay, but if you consider this spherical coordinate system, in the spherical coordinate system, x, y, z axis and different kinds of coordinates also introduced in place of x, y, z, they are theta, phi, r, theta, phi, r, theta, phi. These are called polar coordinates. Polar coordinates, and if we replace xyz Cartesian coordinates using polar coordinates in Schrodinger wave equation, we will be getting a wave function, and the wave function is said to be a perfect wave function which gives two informations regarding the angular part of the wave function as well as this radial part of the wave function. So wave function we will express now onwards by substituting the polar coordinates in place of Cartesian coordinates in the Schrodinger wave equation. By that time we will get a solution of wave function. The solution of wave function is said to be expressed in terms of polar coordinates instead of Cartesian coordinates. That will be having two parts. It's a product of the radial wave function as well as the angular wave function. So what is the solution of Schrodinger's wave equation? Solution of Schrodinger wave equation will be expressed and in which one part of the wave function is called as radial part of the wave function. Another set of the wave function is called as angular part of the wave function, in which radial part of the wave function is said to be completely giving the information about the energy of the electron in the atom. Whereas this angular part of the wave function gives the shape of the orbital as well as the orientation of the orbital along this axis coordinates. Okay, that's why we have written this wave function solution answer here by giving R, this capital R, which is called radial wave function part, which is depending on the magnetic quantum number as well as azimuthal quantum number called orbital quantum number. Whereas the other part of the two functions here, theta is also a part of angular wave function, which is depending on magnetic as well as orbital quantum number, and the other part of this angular wave function is phi. The phi is depending only on the magnetic quantum number. Means here we will come to know the shape and the type of the orbital. Here we will come to know the orientation of the orbital. Okay. So like this, we will define this Schrodinger's wave equation related wave function, how it can be resolved. So if you resolve the Schrodinger's wave equation in terms of this polar coordinate system, you will be getting three different equations. All the three different equations, the solutions are telling one part of the solution with respect to the radius, another part of the solution is said to be with respect to the theta value, another third part of the solution of the wave function is phi. Phi is another polar coordinate. So this is what we called as the solution of Schrodinger's wave equation, making the use of polar coordinates.